right, Gen Chem, today we are going to talk about the electromagnetic spectrum. You're probably really familiar with visible light, and that's probably the part of the electromagnetic spectrum that most of us have the most dealings with. The electromagnetic spectrum is much greater than just the visible light spectrum. If you look at the electromagnetic spectrum here, you'll see that the visible light spectrum is just a small little portion of the electromagnetic spectrum. So visible light, what we can see is just a tiny little part, okay? So we're going to talk about what makes up the electromagnetic spectrum and some of the uses that we have for the electromagnetic spectrum. And then we're also going to talk about the energy that is involved in the electromagnetic spectrum today, because we're talking mostly about energy. So we're going to do this in terms of electrons, and we're going to get into the model of the atom that we ended up with when we had the rings with the different electrons on. And you'll see how this is relevant in a couple of class periods. So there are two variables that relate to a beam of light, okay? These variables are wavelength, and we designate wavelength with this Greek letter lambda. And that is wavelength. Now, wavelength, when we do a wave, I'm just going to draw a wave. We usually measure a wavelength from top to top, or it's called crest. Crest to crest. Sometimes we will measure it from what's the bottom. It's called the trough. So this would be one wavelength, or this would be one wavelength. Now, does it really matter where on the wave we measure from? Not really. It matters that we measure a whole cycle. So I could measure from here to here. That would be a wavelength as well. Okay? So that would be one wavelength. Just as long as we are measuring from the same part of a cycle to the same part of the next cycle. That is a wavelength. Okay? And frequency. Frequency we designate with the Greek letter nu. That is frequency. Now, frequency, let's get some more space here. Frequency, let's see if I have a wave like this, or if I have a wave like this. And I wanted to do this over time. So this is going to be time, and this is going to be time. So I'm going to say that this to this is 1 second. Okay? So frequency basically tells me how many cycles I have per unit of time. And we usually do it per second in terms of wavelengths. So this is just number of cycles per unit of time. So if I look at this top wave, I have 1, 2, 2.5. So I would have 2.5 cycles per second. This wave right here, I have basically just 1 cycle per second. So this would be 1 cycle per second. So notice that the shorter my wavelength is, the higher my frequency is. The longer my wavelength is, the lower my frequency is. So that means the relationship between wavelength is essentially the inverse of the frequency. They are inversely related to each other, which if I put this on a graph, we would get this kind of a graph going on. This is an inverse graph. Okay, so if I had wavelength on one side and frequency on the other, we would have an inverse graph. Okay? So the units of frequency are cycles per second. Okay, cycles is usually omitted in order to make the units cancel properly. So really, we call them per second, or sometimes you'll see it written as per second for frequency. And the wavelength units are usually meters, a length. Okay, so if I have meters per second, when I multiply them together, I would get meters per second. And if I look at the unit of meters per second, that is a speed, that is a velocity. And what speed do these all travel at? These all travel at the speed of light, which is 3.00 times 10 to the 8th meters per second. Now, it's really 299,780 something million. Let's see, 1, 2, 3, 4, 5, 6, 7, 8, right? 1, 2. Let's make sure my units are correct here. We're going to have 1, 2, 3. And then we'll have another comma here. So 1, 2, 3, 4, 5, 6, 7, 8. Okay, meters per second is really the real speed of light. It is so fast. So fast. So just think of it this way. The sun is about 94 million miles away from us. Million miles. Okay? It takes light about 7.5 minutes to travel from the sun here on Earth. Could you imagine traveling 93, almost 94 million miles in 7.5 minutes? That's how fast light travels. Okay? It's super fast. All right. So this is the electromagnetic spectrum. And all of the electromagnetic spectrum travels at the speed of light, which is that huge number that we just wrote, meters per second. So essentially 3 times 10 to the 8th meters per second. Okay, all of this travels at the same speed. Now notice that we have a whole bunch of things on the electromagnetic spectrum. It's not just visible light. I'm going to start with the ones that have our longest wavelength. These also have our frequency that is the lowest, because there are hardly any cycles per second. So we have AM radio waves, shortwave radio, if you ever have somebody that does shortwave or ham radio, TV broadcasts in here, FM radio is broadcast in here, your cell phones broadcast right about here as well. We have radar for our weather systems and our airplane systems. Then we have infrared that feels like heat to us. Then we have our little bit of visible light. Then we have ultraviolet rays. These are the rays that create sunburn. So these are the rays that create sunburn if you are out in the sun too long. That's what makes your skin all irritated and red. Then we have X-rays in here. This is what we use for our medical imaging. Okay, so if you've ever had an X-ray or an MRI or a CAT scan, all of those are in there. And the reasons we use X-rays is they are really good at going through our soft tissue, like our skin, our muscles, our organs, but they're not so good about going through our bone. So we can see the difference between our bone and our on our soft tissues. That's why x-rays are really good. And then we have gamma rays, okay? And gamma rays we get from the sun, we get from radiation, all kinds of things. Now, the thing that is really interesting is a lot of people think that all of this is damaging because, it's called the electromagnetic radiation spectrum. And that word radiation kind of freaks people out. Now, not all radiation is bad. Think about this. If we didn't have the sun, would anything on the earth work? No, we need the sun. We need this. But some of this radiation can be damaging. And let's highlight this. Gamma rays, X-rays, and ultraviolet rays, these are all the type that create what we call ionizing radiation. So these create what we call ionizing radiation. Okay? And that can be dangerous. And that's why when you're out in the sun too long and those UV rays hit your skin, it creates damage in your cell because that ionizing radiation can knock or take an electron out of an atom. It has enough energy to take electrons out of an atom. And if those electrons are knocked out of their orbits in an atom, it creates an ion, and that ion can create mutations. And if that mutation is in the right spot of your cell, the right gene on your DNA, it could cause cancer. So all of these gamma, X-rays, and ultraviolet rays are enough energy to knock that electron out of orbit and create an ion. And if that ion's in the wrong spot, it can mess with your genes. Okay? So let's look at the wavelength of some of these different things. So we want to look at the wavelength. So we have wavelength. We're going to put this in meters. So what's the wavelength of AM radio? It's right here. It's at 10 to the 4th meters. So 10 to the 4th meters is really about 10 kilometers. So 10 kilometers for one wavelength. It's a really big wave. And that's one of the reasons why AM radio is able to travel such distances. Okay, FM. Let's look at FM. The wavelength is about 1 meter. Okay, which travels faster, AM or FM? We said this all travels at the speed of light. The speed of light is constant, so they're both traveling at the same speed. They're both traveling at the speed of light. So they are traveling at the same speed, the speed of light. Okay, which has a higher frequency? Okay, remember we said that the frequency is, proportional to the opposite of the wavelength. So if AM has bigger wavelength, it's going to have lower frequency than FM. FM has shorter wavelength, so it's going to have more frequency. So FM has higher frequency. And I can't spell. Which one has higher energy? Now, I don't know if I said this, energy goes up as we go across the magnetic spectrum. So if we go across the magnetic spectrum and start here and go up, energy is the biggest as we go from right to left. So which one's going to have more energy? FM. FM is farther along to the left. So the FM is going to have more energy than AM waves. Okay? What's the wavelength of UV? So let's look at ultraviolet. Ultraviolet looks like it's about 10 to the negative 8th. So that is less than a nanometer, or about a nanometer. It's about 10 nanometers, actually. Okay, what's the wavelength of visible light? If we look at visible light, we have from about 370 to about 780 nanometers. So that's about 370 to about 780 nanometers. And nanometers are 10 to the negative 9th meters. Oh boy. So they're really, really small. So there are a billion nanometers in 1 meter. Okay? Which travels faster? Hopefully you realize it's the same thing as this. What travels faster than AM or FM? What travels faster? UV or visible? They're all traveling at the same speed of light. C equals speed of light. And C is the letter that we use to designate the speed of light. Right. Which one has a higher frequency? Remember, as wavelength goes shorter, frequency goes up. Which one has the shorter wavelength? UV does. So it's going to have a higher frequency. Okay, which one has more energy? Remember, the farther to the left we go on that diagram, and UV is farther to the left than visible light, it's going to have more energy. Remember, UV is the first type of electromagnetic radiation that has enough energy to cause ionizing radiation. It causes a sunburn. Okay? That has enough energy to be ionizing. Okay, what's the approximate wavelength of green light? Let's look. So green's right in here. So here's 500 nanometers and here's 600. So right here, I'd say about 510 to about 560 are the greens, nanometers. So I'd say about 510 to about 560 nanometers is what we would say is green light. Let's look at violet light. Violet light, purple. So we have about 370 to about 410 is violet light, what I would consider violet light. So about 370 nanometers to about 410 nanometers is violet light. What about red? Let's look at red. Red's going to have the biggest wavelength because it's the lowest energy. So I'd say for red, we've got about 670 to about 720. 670 to 720. Okay, so let's rank green, violet, and red in order of frequency. We wrote down the wavelengths. So remember, frequency is inverse to wavelength. Okay, so as the wavelength is larger, the frequency goes smaller. So if we want increasing frequency, we want the smallest frequency first. So that means the largest wavelength. Which one has the largest wavelength out of green, red, and violet? Red does. So red has the lowest frequency. Then our next biggest is green. Then our highest frequency is violet or purple. Okay? Rank green, violet, and red in order of energy. Well, frequency and energy are pretty much the same. So frequency, well, they're not the same, but they're in the same order. So as frequency goes up, energy also goes up. So guess what? It's going to be the same list. So red has the least energy, then green, and then violet has the most energy of our visible light. Okay? So I hope you learned a little bit about the electromagnetic spectrum today. And if you have any questions or concerns, please let me know. Please email me. We'll talk to you later. Bye.